Good morning, everyone. Let's go over these questions here quick and then we'll start our day. So the goal is to evaluate integrals just by finding the antiderivative. And this is based off of the fundamental theorem of calculus work that we had done the unit before. So when I see a problem like this, the integral of t to the negative fourth power, remember that could also be written as 1 over t to the fourth, which a lot of times it's written that way, and then we have to turn it back into a problem that looks like this, because now we can undo the power rule. So just remember, it could have been written like this as well, but what do? We always add 1 to the exponent. So when I do that, I'll get t to the negative third. But if I put a negative third up top, I got to compensate for that, and I have to divide by a negative 3 or times by 1/3, and then a negative 1/3. And then remember, there are no bounds here, so we're going to put plus c. And what you can always do with your answers, you can take the derivative of this to get back to where you started. So nothing super crazy with that one. It's just kind of undoing the power rule. Number 2, what we want to do first is we have everything divided by x. And that's kind of our focus at the start of this newer unit. And I call it a new unit, but we're doing unit 6, part 2. So we're still using all the skills from the last unit. But what I would do first is algebra. And now you could do this in your head, but what am I doing? I have a single term on the bottom, and in that case, it's like I'm undoing the addition of fractions property, right? I'm dividing by an x, I have a common denominator, so I could combine them to get this term, but if we think of them as separate fractions, now we see an x reduces out of this term. I cannot reduce the x out right away. If I do that, the 1 has to still be over an x, because x is dividing all these terms in the numerator. But when I do that, I actually end up with e to the x plus 1 over x, and now it's two antiderivatives that we're pretty familiar with. Whose derivative gives me e to the x? It's just e to the x. And whose derivative gives me 1 over x? This is a big one. Make sure when you put ln, it's ln of the absolute value of x. And the reason why is if we don't have the absolute value there, the natural log can never be a negative number. So then we're not kind of honoring the domain of that function. And that's what we have to do with the absolute value bars. All right, and then number 3 is just what happens when I have limits. And by the way, all this stuff is coming up this unit, so we want to make sure we're really good with it. Number 3 is basically the same work you did in number 1. The only difference is it was a negative exponent number 1, here it's a positive. So I'm going to add 1 to the exponent. I get x to the fourth, but if I put a 4 up top, we got to compensate for that and put a 4 up front. But then we still have this integral from 4 to negative 4. Well, that integral is the antiderivative evaluated at the upper bound minus the lower bound. So what we're going to do then is we're going to plug in the upper bound first minus the lower bound. Okay, and then we're going to simplify. One of the things you might notice right away, and this is up to you if you notice it, but notice this 1/4 is an extra power of 4. So the 1/4 and the 4 could reduce out if you wanted it to. Because if I do it to the 4th power, 4 to the 4th power, I think is like 256. And then if I divide that by 4, I get 64, which is 4 to the 3rd power. So this is just a quick little recognition of that. This is an interesting one because the negative 4 to the 4th power would be a positive 256, and then we end up dividing by 4, which is 64, which is also 4 to the 3rd. But notice you end up getting the same thing. If you did it without those properties, you would end up with 64 minus 64, and you would still get 0. Okay, you're going to see why those skills are important today and leading up to this week. Before we do that, I want to make sure we touch base on a couple of different things. Okay, so Today is the 16th. It switched. Today is hours 246, and you know that because you're here. Um, Tomorrow is Wednesday. You're going to have to watch an Ed Puzzle video again and take notes. And it's crucial that you do this Ed Puzzle video to set us up for success on Friday. All right, next week is I will see you guys again on Tuesday. We had to do this kind of for the way that the end of the hours, the hours that we met ended up even out. But next week you do not have school on Friday. By the way, this is Friday. And then here's the interesting part. You actually got 2 days taken off of this trimester. So your last day of school for second trimester is Tuesday, March 2nd, which means you get an extra 2 or 3 days of spring break. The downfall on that is if you're behind, you have less time to get your work in. And I'm not going to be doing grading over these days. These are teacher prep days to get ready for third trimester. So, with that being said, I want everybody to understand this. You have to have all work in by Friday, February 26th. Okay? All late work, all work is due. Now, we are going to have a test on this day, and it's going to be on Chapter 6, Part 2. So it's just a really short test over the last week and a half here. However, it is summative, and that's something that will go in kind of against your grade. Any questions currently about this end of trimester 2 right now? Okay. I can always come back if a question pops up. I do want to talk to you quickly about third trimester, and just third trimester is going to be much different than this. See if I can find it. Here we go. It's going to be different, and I'm not sure if this was shared with you completely, but I want to show it to you now. Okay, so really quick, third trimester, we're going to be talking about hybrid for third trimester starting right after spring break. Depending on which category you're put in, you might be with us completely online, or you might be in group A or group B. But here's the idea of how it's going to work. It's going to kind of be similar. Actually, I take that back. It's not. Look at this. Now we're going to go from hours 1, 2, 3, and then hour 1 is going to start obviously at 8:10 in the morning, and then hour 2, and then hour 3, and the next day would be hours 4, 5, 6. So there's a switch in which hours you have linked together. I don't know if that's a good thing or bad thing. It depends on your schedule. And that's in the morning. That's synchronous, so everybody would be with us either in the classroom or on Zoom. And then the afternoon, this is the big shift. I want to make sure everybody understands this, right? In person, if you are in the hybrid model and you're showing up at Tartan, you have to go back to your classes, okay? You have to go back to your classes in the afternoon. So if it's a 1, 2, 3 day, so you go to 1, 2, 3 in the morning, then after lunch, you're going to go to 1, 2, 3 again, and you're going to go there for about 35 minutes in some of these cases, and some it's 40 minutes or so. And the reason for that is that's where you can go get teacher help. What we're going to be doing in calculus in the afternoon session is those students that are in class with us, or those who choose to join us on Zoom for that time, we're going to be doing some AP practice problems. Now, there will also be some days where we just work on our homework, but I do want to know, or want you to know, that there's a shift in how we're going to approach calculus third trimester. And it's a little bit more. It's more demanding because we have to get ready for the AP test. And then Friday, all groups will be at home learning, doing asynchronous work. Friday is going to be kind of like our Wednesday currently. All right. Now, I'm not sure if you're in the same hybrid group as you were last fall. I think that might switch because the reason why is because the classes switched, so they have to balance it out. So I'm not going to say one way or the other if you are in Group A or Group B. That information, to my knowledge, is going to be emailed out shortly, probably before spring break. So that way you have a week to think about it and go from there. Um, but I just want to make sure that everybody understands how this schedule is going to work. So here's kind of the first week of spring break. So we're going to start on Monday, March 15th, and we're going to go hours 4, 5, 6. So that's on Monday. So we go 4, 5, 6 in the morning. And then those of you that are in Tartan on that day, you have to go back to your 4, 5, 6 in the afternoon. And attendance is required for those afternoon time sessions. You cannot go back. Now, if you are not at Tartan on that day, then you are expected to just do the homework and you do not have to attend the afternoon sessions. Okay? That's your asynchronous learning. That's where you do your homework or whatever you would do normally. You cannot leave after your morning classes. If you leave after your morning classes and you do not show up to the afternoon session and you're supposed to, then you're counted absent. It's not possible to leave. That discussion was already brought up, and there's no way we can manage it if certain kids leave and certain kids don't. Okay? So please understand that. And then what we would do, so Group A, if you're in Group A, you would go to school Monday, Tuesday. And notice we do alternate the hours. Monday is always going to be 4, 5, 6. Tuesday is 1, 2, 3. And then Wednesday, we would repeat that cycle for Group B. So Group B would come 4, 5, 6 in the morning and the afternoon, and then 1, 2, 3 on Thursday. And then on Friday, everybody would be doing their asynchronous learning. To get into the logistics of this, the reason why we had to do this is Tuesday and Thursday, we had to have hours 1, 2, 3 for the students that go to 916. And that's true for both people in our district, North and Tartan. So, right now, March 30th is slated for MCAs and ACTs, and that's 10 and 11th graders, and then all 9th and 10th graders will be asynchronous that day. And you can just see that as we get into April and May, it's still the same schedule. 4, 5, 6 is always going to be Monday. 1, 2, 3 will always be on Tuesday, and that's Group A. And then Group B would have Wednesday, Thursday, same thing. So that's where we're at. And then we get done officially June 3rd. All right, so the reason why I want to show you that is also to help frame your mind for what's happening third trimester calculus, because you guys need to know what the expectations are. And I want to make sure that you are in a spot of, if you're planning on taking the AP test, you are going to have as much practice as possible. So what can we expect for third try? We have to cover 2 units. We're going to cover Unit 7 and Unit 8. And my guess is that's going to take us kind of mid-April. All right? So if you think of that, mid-April, we'll be done with calculus. All right? And then what are we going to do for the rest of the time? We're going to review. Now, with that, we're going to review multiple choice style questions and free response. The free response questions are ones where you're going to have to either do them online and submit them, or I'm going to have you handwrite them, because we are focusing a lot on notation. If you don't have perfect notation, you could miss a ton of points in the free response questions. Third trimester calculus is going to be tough. It's going to be challenging. If you've been really working hard all year, first and second trimester, you'll be fine. If you've taken a back seat for first and second trimester here, and you haven't been watching the videos, you've been somehow getting answers and submitting them, or you've sometimes, if it's my work that you just straight copy down, because that happens, I understand that, and you're not fully dedicated, I think third trimester is going to be extremely challenging for you. Okay, I do want you to know that our summative pieces, our tests, and maybe even quizzes, will be on AP Classroom, and they're going to be practice AP tests. Okay, and there's going to be some where we do a full multiple choice portion in class and a full multiple choice part the next day, and then free response. And sometimes that takes a full week. But your grade is going to be based on that. And what does that mean? That means units 1 through 8. That means you have to have mastered some of the knowledge from units 1 through 8. Now, if you've been fully kind of committed to calculus this year, that's why the review is going to be important. We're going to cover some things really quickly, and you'll start filling in any of those holes you might have had. However, if you've really kind of had a relaxed approach, we're not going to kind of reteach complete new concepts. We're just kind of building off of what we already know and hopefully giving you guys the confidence that you need. So I want you to think about your commitment to third trimester calculus. If you're somebody that is just trying to jump through the hoops and get a grade, if it's a P, I don't know if third trimester calculus is for you. Because I don't think you're going to be able to be successful even with just getting a P unless you're fully committed. So I do want you to know what's at stake with this third trimester. If you're currently at an A or B in this class, you're fine. You are absolutely fine, and you're going to be doing well. If you're at a C, I would say you have to step your game up. If you're at a P or a no credit, honestly, I don't know if there's, unless you make drastic changes to the way that you approach calculus, I'm not sure how much you'll get out of third trimester. So I want you to be aware that if you have any questions on whether or not third trimester is the fit for you, please come talk to me in my office hours, send me a message, and we can chat about it. I'll give you my honest opinion on where I think you're at this trimester based off of what I've seen. Okay, so we are going to do a couple of problems today. We don't have a ton to work through today, which is good because that is going to give some of you guys a chance to get caught up on some things and do some reflecting. All right, if you would like, you might want to take a screenshot of this because we're going to just kind of talk about it. Otherwise, this is in page 439 in your textbook. All right, we are not going to have time to write all of this down. That's why I'm referring to this page. However, what this is this is a table of basic integrals. Now, sometimes you can just look at this chart and there's your answer, right? Other times you have to be more creative. And that's probably where they're going to test you is the more creative side, but you need to know these skills. Well, if we think of what an integral is, it's undoing the derivative, right? So if you've mastered your derivatives, you should have your integral formulas mastered as well, right? So let me just show you quick. I'm not going to go through all these, but if I have a blank integral, or remember, you can always put a 1 there. The integral of 1, whose derivative gives me 1? It's always x. Right? Or if I have this, whose integral gives me 5, that's 5x. And then we always put plus c, because if there aren't any bounds, or the limits, top and bottom, then we have to account for that constant. This is just the power rule, right? If I have x to the -4th, like we did in the warm-up, what did we do? We added 1 to the top. And if whatever I put in the top exponent, I have to divide by that or multiply by the reciprocal. Okay, so this is just undoing the power rule for this one. And this was the very special one. Remember, x to the -1. The reason why I can't add 1 to this, because if I do, I get x to the 0, and anything to the 0 is 1, and that doesn't give me the original function. So x to the -1st power is the special one, and that's where we write it as 1 over x. And notice the absolute value here. So this is a big one. I see this one test quite often on the AP exam. Right? And the integral of e to the x is always itself. We're going to talk about this one with a couple examples down here, but I think this is the tough one. If I have a to the x, where in this case x is the variable and a is a constant, so this would be like 3 to the x, then the antiderivative of that is itself divided by the natural log of whatever the base is. Okay, so we're going to go over that one. Here's all the the trig functions, right? Whose derivative gives me sine? It's negative cosine. Whose derivative gives me cosine? Negative sine, and so on. And then the other two, and these are the two that you have to know. You do not have to know inverse secant. This one is just here in case you want it. But remember when we learned the derivative of inverse of sine, its derivative was 1 over the square root of 1 minus x squared. And tangent, the inverse tangent derivative was 1 over 1 plus x squared. So the integrals are undoing those. All right, so let's use the chart to evaluate some integrals. And you'll notice they're not all identical to what you see. And that's where you have to understand the properties of integrals as well. So I would write these ones down here. And we're going to go through them shortly. So let's do them one by one here quick. I'll scoot this up just a little bit for now. Okay, when we look at this first one, I have the integral of 5 times 1/2 to the power of x. And you got to kind of pay attention to what the function is saying. Notice that 5 is a multiplier. So one of the big skills that we want you to learn is if you have a multiplier in an integral, you can pull that out. Because now we're looking at, well, wait a minute, this is a to the power of x. That's what I have right here, a to the power of x. Well, what is a? A is 1/2. So if I know what a is, I'm just going to put it right here in the function. And then that multiplier 5 is just going to come out. Okay, so 5 is your multiplier. And then the antiderivative of 1/2 to the power of x is 1/2 to the power of x divided by the natural log of whatever a is. In this case, a is the base plus c. Now I might clean this up, and that's something you also have to be aware with, is once you take the antiderivative, if we were writing it by hand, this would be good enough. But if it was a multiple choice question, it might be written like this, where they take the, I don't like the way that looks. They take the 1/2, the natural log of 1/2, and they divide it under the 5, and then they could put this off to the side. And those are equivalent. It's the same thing. Okay? And this came from just knowing this rule. So I'd make a special note of this rule. This one is one of those ones that students tend to forget. And that's actually kind of the goal with these 3 examples. We're doing the ones that aren't as common. All right, let's look at this one. I have the integral of 7 divided by the square root of 1 minus r squared dr. Well, the first thing I notice on this problem is that the 7 is not present in any of these rules that we had up there before. That's a constant, right? I could pull the 7 out. And if I do that, there's a 1 in its place. And now I'm left with 1 divided by the square root of 1 minus r squared. And I'm hoping that that part, you're thinking, oh, wait a minute, I've seen that derivative before. Whose derivative gives me 1 over the square root of 1 minus r squared? And that goes right here. Now, it isn't an r squared, but it's an x. That's exactly what we want. So I know that this portion will turn into the sine inverse of r. And then the 7 is just that multiplier. Okay, so 7 would stay. And then this turns into the sine inverse of r plus c. And that's as far as we want to write this. Remember, when we have the inverse, this -1 is not the same as like this -1. that we had over here. So just be careful with that. All right, and then the last one here is even trickier, but you'll notice the 5, the 7, those were constants, right? Those are something that everything was being multiplied by. In that case, we can just factor that out and put that out in front. And the same thing is true here. This is just hidden a little bit. You'll notice I've got a 1 up top, but then I could factor out a 4. Now, I'm going to show you this just so you guys understand why I would do this. I've got a 4 on bottom in both spots, which means I can factor the 4 out. But then I've got a 1/4 that can actually be taken out. Now, if I take away a 1 from a 1, there's still a factor of 1 left over up top, right? But on bottom, I get t squared plus 1, which you'll see why I'm doing this. I'm going to put, because it's addition, I can flip the spot of the 1 and the t. Okay? And the reason why I'd want to do that is now I'm thinking, well, whose derivative gave me 1 over 1 plus x, or 1 plus t squared? That's the exact same thing we had right here, 1 over x squared. Now again, if this x squared was written first, like we had originally, that's fine. It's the same thing, because addition, you can add in multiple different directions. So whose derivative gives me 1 over 1 plus t squared? It's exactly the same. It's just tangent inverse. So the 1/4 would be out there as a multiplier, and then the antiderivative is tangent inverse of t in this case, plus c. And you'll notice you always have that plus c when you don't have limits. Now, hopefully, none of this is brand new. It's more of some trickier ones using this table on page 439. Okay, so if you have time, I would either put a little post-it note in your textbook so you can always refer to this, or do a screenshot, maybe even print this out if possible. But we technically alluded to this already, so there's nothing new that we've learned here. What I'm getting at, though, is what if we have these skills, and now all of a sudden it's a little more challenging than just the fact that my antiderivative is not in this chart? What if the chart is more than just a common number factored out, and then we just look exactly what's in the chart? And that's what this new unit is all about. Okay, so like right here, I don't have a rule on this chart that specifically gives me e to the 2t minus e to the negative 2t. But we're going to start introducing something here. And I do want you to know that what we're doing in the next couple of days takes practice. It is not something that you're going to get after one example, because there are so many different variations of this method that you need practice, 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 practice. So if you're not watching the video on Wednesday, if you're not doing the homework, you're going to be really in a rough spot. Okay, so let's take a look at this. Now, the first thing I notice is I've got functions up top. They're both e to the power of something. And then I'm dividing everything by 2. Well, that divide by 2 is the same as timesing by a 1/2. So what I'm going to do is I'm actually going to pull that 1/2 out. And then I have 2 antiderivatives. Now, we know that if it was just e to the t dt, we know that that derivative or antiderivative is exactly the same, right? So we know that rule from before. However, the new part, and the part that's going to get a little more challenging, is what happens now if I have something more than just a t up top. And for right now, the only way that we know how to do that is to use guess and check. Here's what I mean by this. Okay, I know that it's going to be e to exactly what's up here, right? However, if I take the derivative of this, we would have to times by 2, and the derivative would have an extra 2 coming out, and I don't have that extra 2 right here. So what we have to do is we have to compensate for the fact that that would have its derivative going backwards, would have an extra 2. So in that case, I'm going to multiply by the reciprocal of this derivative up top. So if the derivative was 2, I'm going to multiply by 1/2. Okay? Now, I am going to put this in parentheses because this 1/2 originally that we pulled out is multiplied by the answer of this whole thing. So now I have subtraction of exactly what I think is going to be there, e to the negative 2t. But if I was to undo this and go back by taking the derivative, I would have a negative 2 coming out from the derivative of this exponent. Well, I don't want that negative 2. I want to compensate for the fact that a negative 2 would be present. So I'm going to multiply by the reciprocal of that, and we usually put it out in front, which would be a negative 1/2. And again, if you're not confident in that part, take the derivative of the red. You'll see the negative 1/2 right here will reduce out with the negative 2, and I'll get back right to where I started. And then we can simplify this negative and this negative would be addition. And if you have two options, you could distribute the 1/2. So 1/2 times 1/2 plus 1/2 times 1/2. Now notice these are different powers. Oops, sorry, this should be a 1/4. So I'm just going to leave it like this. Or you could have really taken another 1/2 and factored it out, or you can factor out a 1/4 here, and it could also be written this way. Okay, I know what you're thinking right now. I don't like this, right? I don't like the fact that I had to guess and check for these two answers. And that's true. We shouldn't have to guess and check. But I wanted to show you the possibilities of these pieces because we're not actually going to do guess and check. We're going to learn another method that involves what we basically did was we undid the chain rule, or the reverse of the chain rule. And there's something special we're going to do with that. So, if this problem frustrated you a little bit, that's okay. It was meant to do that. It was meant to say, we don't have this exact rule because I had a 2t and a negative 2t. And how do we get those coefficients out in front? Now you can think of undoing the derivative of those, and guess and check will work for this one. But what about our last one here today? Okay. We don't have a rule, or we don't have somebody's function, somebody's derivative, that is tangent squared x times secant squared x. This is not just one single function's derivative. So what we need to do is we need to come up with a method that isn't guess and check. And you have to hear me out on this. What we're going to do is we're going to introduce something called substitution. And I'll give you a little hint. If you remember when we started doing derivatives, and it was all just, hey, if it was exactly like this, here's the rule and here's the derivative. But then we introduced the chain rule. And once we learned the chain rule, the derivatives got more challenging, right? And we always, forever, have to think and use the chain rule whenever it's applicable. Well, same thing with integration. Right? Since the chain rule is always present, we have to be able to reverse the chain rule. So when we say U substitution, what we're actually doing is we're reversing the chain rule. Now, hear me out on this because this is a little bit tricky. Our goal is to pick a U value. Now, we call it U substitution. You could really use any variable you want. You could use W, X, Z, Y. We probably won't want to use X because that's the variable we have here, but you can pick any variable. But I need to pick U to be one of these functions. And our goal with that function is we want to figure out if I pick the U, we're then going to take the derivative of U. And we want both of these items to be present in this function. So hear me out on this. I'm going to give this original equation a little bit of a rewrite. And I'm only going to do it to the tangent part. Remember when I have tangent squared, I can think of that as tangent and then squared. And then you'll see why in a second, but I'm going to rewrite secant squared as a separate color. And then the dx is a separate color. So watch what happens. I want to make this easier to deal with because right now we don't know this. This isn't a rule that we know. So I can't actually apply any integration method that I know. However, I'm going to take the fact that if I let U be equal to a part of this function, I'm going to let it be tangent. Okay, now watch what happens. What did we have? If I replace tangent with U, that makes this part easier to think of and deal with. But what happens to the secant squared dx? Well, now, if this is U, du is the derivative. The derivative of U. That's what du means. Well, let's think of this. If U is tangent, we know the derivative of tangent is secant squared x, and because we're taking the derivative of x, we have a dx after that. Well, look at what we have then. If we're replacing U with tangent, and then the derivative of U is secant squared, we're going to replace that with du. Okay, now notice secant squared dx, that whole thing in green is exactly what du is equal to. Well, why would we do something like that? Now, look at this integral. This is an easier integral, and that's the goal, right? U substitution made this integral easier. And that's the goal, right? Because now I can take the antiderivative of this pretty quickly, right? We're going to undo the power rule. So I'll have U to the third power. But if I put a 3 up top, I have to put a 3 out in front, or 1/3 out in front, plus C. Notice the integral symbol went away because I took the antiderivative. But our original problem was written in terms of x, not in terms of U. So all we have to do then is take this piece and replace it. Instead of U, we know U was tangent of x. And there's our answer. Okay. Now, first time you see U substitution, you're thinking, what in the world did we just do? Why did we do it? How does it work? It takes practice. It takes a lot of practice to get this done. So what I want to show you is let's check. By checking our answer, you're going to see where this u substitution came from? And remember, how do we check? Well, we take the derivative of both sides. Oops, I've got an x right there. Change that. Right? If I take my answer and I take the derivative of that answer, I should get back to where I started. So we're doing the chain rule here to take the derivative, right? We're going to keep the inside, and this 3 is going to come down. Well, 3 times 1/3 is 1, which we don't have to write. And then it's tangent of x, and we take 1 away. However, when I take 1 away, I get a 2. And then we have to times by the derivative of the inside, and the derivative of tangent is secant squared. And then the derivative of the plus c is 0. Right? We don't put the 0 here. You can if you want to. And then if I clean that up, I don't need the 1 here. And instead of doing tangent squared, I can put the squared at that spot. And notice the derivative is right back to where we started. So I think it's easy to see when you check, it's easy to see where that derivative comes from. And u substitution is what allows us to find that. Okay? Now, the video on Wednesday, Mr. Waffler did it. You are expected to watch that and take some notes because it's going to introduce more u substitution. I knew we didn't have a ton of time today to go over that, so I wanted to just introduce that. I want to show you one last thing here quick, because this happens every year, so don't write this. Please do not write this. But what if I rewrote this the way, or what if I tried something else, right? What if I tried this, where I tried to say, oh, well, wait a minute, why can't I let u equal secant of x? And then du would be the derivative of secant, right? So what if I accidentally picked the secant instead of the tangent? Well, you're going to start to learn that, watch what happens. The derivative of secant is secant tangent dx. Now, our goal is, if I'm going to replace the u with secant, so this part would be u, so that'll be u squared, then I have to take the dx, and the tangent squared of x has to be replaced by whatever this is. And notice, secant tangent x doesn't exactly replace this, right? It might, this tangent would replace one of these, and this dx would replace it, but I would have, and this is going to be kind of a mess, I would have a tangent x left over, and then I would have a secant, and then I would have a du. The du would only replace, the du has an extra secant in it, and you'll notice this is way more confusing. I have x's and I have u's mixed together, and I don't have everything combined. So you can pick the wrong u value, and it will make things miserable. So if you start working on a problem like this and it's getting more confusing, basically, if you don't see the derivative represented in the original integral, that means you probably took the wrong u. And that's something I just want you to be aware of over the next couple of days. All right, so here's what we have. Part of today, because we don't see each other, I don't see my hours 1, 3, 5 until Thursday. And I didn't want to get too far ahead in this class and then have you guys be kind of like burning daylight at the end. I want to balance my classes out. So what I did was I just kind of introduced this chart, which we've kind of already known, and we introduced u substitution with one example. So here's what we got for today. I want you to, if you have not done so, your goal today is to complete the Chapter 6 test. Okay? If you have not watched those Ed Puzzle videos from the last 2 Wednesdays, you need to go back and do that. Okay? And then tomorrow, there's a new Ed Puzzle video. You have to do this. If you do not watch that video, when we see each other again on Friday, I'm going to assume that you watched that and you've already been exposed to 6 or 7 different types of U substitution problems, because we're going to jump right in and go pretty quick. So this is what I mean by, if you're not watching the videos and doing what you need to do, then I'm not sure if you're ready for third trimester calculus. Some of you are doing exactly what you need to do, but well over half of us in this hour are not watching the videos on time and not getting things done. So that's my concern. That's it for today. There is no new homework. If you've done everything you need to do, then you've kind of earned the right to have a little bit of a relaxing day today. But those of you that need to get caught up, please do so.